This is 9.7, Part 2. All right, so we just talked about the remainder of a Taylor polynomial and Taylor's theorem. And so let's do an example so that hopefully will make a whole lot more sense. This is example 4. Let's see if we can find piece of 3 for f of x equals sine of x. And I want to find a Maclaurin polynomial. So if they say Maclaurin polynomial, that immediately means c is 0. Okay, so kind of keep that in mind. So we're going to need to do that to know f of x, f prime of x, etc., second derivative. And we're going to stop, because it's a third degree polynomial, with the third derivative. So the derivative of sine is cosine. The derivative of cosine is negative sine of x. The third derivative is negative cosine of x. Then, when c is 0, find all of those values. So sine of 0 is 0. Cosine of 0 is 1. The opposite of sine of 0 is 0. And the third derivative at 0, opposite of cosine of 0, is negative 1. And so the Maclaurin polynomial piece of 3 of x for sine of x will be f of 0 over 0 factorial times x minus 0 to the 0. And I'm not going to say x minus 0 each time, x minus c, because it is just x each time, plus f prime of 0, which is 1, over 1 factorial times x to the first, plus, oh, I wrote 0 back there. Hold on, I made a mistake. I may have said 1, but I'm pretty sure I did, but I wrote a 0. It's a bit ahead of myself at that stage. No, I wasn't. That's right. What am I doing? Wow. I think I must be getting tired. Okay, that was correct. It is 0. Pardon my mess up there. Plus f double prime of 0, which is 0, over 2 factorial x squared. And then the last one, because it's a third degree polynomial, is f triple prime at 0, negative 1, over 3 factorial x cubed, which simplifies to be 0 plus x plus 0 minus x cubed over 3 factorial. Okay. Now, I want to use Taylor's theorem to approximate sine, the actual function value for sine, at 0.1 using this polynomial. So sine of 0.1 is approximately what we get when we put that 0.1 into our polynomial. This is kind of like when I had you graph and I had you toggle between, for x equals 0.1, toggle between the values, and you saw different y values that popped up. We're calculating the polynomial answer for x equals 0.1. That's what we're doing here. So that's going to be 0.1 minus 0.1 cubed over 3 factorial. Okay. So that is approximately 0.099,833. Okay. And now let's determine the accuracy of that approximation. So sine of x, which is going to be our polynomial that we found, plus the remainder, having stopped with p sub 3, it's the remainder sub 3 of x. Okay, so the actual sine of x answer is our approximation plus something, which that something could be positive or negative. And according to Taylor's theorem, that something is the next thing, which would be the fourth derivative, the n plus 1 derivative, evaluated at z divided by 4 factorial times x to the 4th, where z is a number between x and c. Okay. So our x in this problem is 0.1, and our c in this problem, because it's a Maclaurin polynomial, c is 0. So z is between 0 and 0.1. Okay, c is 0 because it's Maclaurin, and 0.1 is the number we're trying to find an answer for. So that's our x. So if we go back up here, or take what we did up there and go one step further, what is the fourth derivative of that function? Well, third derivative was negative cosine of x. So the derivative of that is going to be the opposite of negative sine of x. That is sine of x. And so our error, which is going to be positive, because that's not going to be a correct answer as is, will be the remainder evaluated at 0.1, which is sine of z. So I've taken that fourth derivative expression up here and put z into it, where the fourth derivative we just calculated was sine of x, so sine of z over 4 factorial times x, which in this problem we've let x be 0.1 to the 4th. Okay, and because the sine of z never goes bigger than 1, as a worst case scenario, we could assume that it takes on the very biggest possible value it could have, 1, and I could put a 1 in, and that expression is definitely bigger than whatever the sine of z might be. Okay, and so if you put that in your calculator, that is approximately 0.1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5 zeros, and a 4. So what that means, the implication, is that this answer we got, the 0.099833, which is less than the actual answer for sine of 0.1, is approximately, that sine of 0.1, our answer plus the remainder part evaluated at 0.1 which is less than 0.099833 plus what we just calculated, the 0.000004. Or in other words, our answer for sine of 0.1 is somewhere between 0.099833 and 0.099837. And I got that number by adding these two together. And so we don't know exactly what sine of 0.1 is from this polynomial estimation, but we do know that it's definitely between those two values. Okay, so let's move to example 5, where we're going to find Taylor polynomials, p sub 0, a 0-degree polynomial, p sub 1, first-degree polynomial, p sub 2, etc., p sub 3, third-degree polynomial, p sub 4, fourth-degree polynomial. Oops, that's it. That's the last one we'll find. For f of x equals ln of x centered at c equals 1. Okay. So, f of x being ln of x means that the first derivative of f is 1 over x. And that form is great for some things. We might want to think of that as x to the negative first, just in case we need it. That form is also true. Then find the second derivative, because we're going all the way to p sub 4. Eventually we're going to need all of these derivatives, so I'm just going to go ahead and find them. The derivative of x to the negative first is negative x to the negative second, which is, if you need it, negative 1 over x squared. The third derivative of f is negative 1 times negative 2, so 2x to the negative third, aka 2 over x cubed. Either of those expressions is fine. You'll notice that for derivative purposes, I like the negative exponents. For substitution purposes in a second, I'd rather not have them. Anyway, the fourth derivative is negative 6x to the negative fourth, aka negative 6 divided by x to the fourth. Okay, now we know that c is 1, so we're going to need to calculate f of 1, f prime of 1, f double prime of 1, etc. So we're evaluating our function and all of its derivatives through the level that the question asks us to go, evaluating each of those at c, which in this problem is 1. Okay, so natural log of 1 is 0. 1 over 1 is 1. Negative 1 over 1 squared is negative 1. 2 over 1 cubed is 2. Negative 6 over 1 to the fourth is negative 6. Okay. So, the 0-degree polynomial is simply f of 1 over 0 factorial times x minus c to the 0. F of 1 is 0. 0 factorial is 1. X minus 1 to the 0 is 1. And so that answer is 0. Okay, we're supposed to then find piece of 1. Without writing that first part again, it's going to be that last answer plus the next term, which is f prime of 1 over 1 factorial times x minus 1 to the first. So each time we're going to take the polynomial we have up to that point and just add one more term to get the next higher degree. Okay, f prime of 1 is 1 over 1 factorial is 1, so 1 over 1 is 1 times x minus 1 to the first, that's x minus 1. Okay, piece of 2. Take everything we have so far, which is x minus 1 to the first so far, plus the second derivative evaluated at 1 over 2 factorial times x minus 1 squared, which is x minus 1, and the second derivative at 1 is negative 1, so minus or negative 1/2, so 2 factorial is just 2 times x minus 1 squared. And that plus a negative we could certainly write as subtraction. In fact, I will on the next line. Piece of 3 of x is going to be our answer so far, which is x minus 1 minus 1/2 of x minus 1 squared plus the third derivative evaluated at c, which is 1, over 3 factorial times x minus c, which is 1, cubed. And so piece of 3 of x is x minus 1 minus 1/2 x minus 1 squared. Okay. So the third derivative evaluated at 1 is positive 2. 2 divided by, see, 3 factorial is 3 times 2 times 1 is 6. So 2/6 reduces to 1/3 x minus 1 cubed. Okay. And the last one we're supposed to find, thank goodness I got to the point where I can come way over here because I might need it. So piece of 4 of x is everything we already have plus just one more term. Okay, so that's what we have so far. So now we're going to add f, fourth derivative of f, I should have said, evaluated at c, which is 1, divided by 4 factorial times x minus c, which is 1, to the 4th. Okay, so piece of 4 of x, pen kind of garbled a little bit. Let me try again. So p sub 4 of x is x minus 1 minus 1/2 x minus 1 squared plus 1/3 x minus 1 cubed plus, okay, so the fourth derivative of our function evaluated at 1 is negative 6. 4 factorial is 24. This time I'm writing it out instead of doing it all in my head so that you can follow perhaps this last one really, really well. And so simplifying, this is x minus 1 minus 1/2 x minus 1 squared plus 1/3 x minus 1 cubed minus 6 over 24 reduces to 1/4 x minus 1 to the 4th. Now, if I asked you to, could you find p sub 5 without going through all that work? Just curious. And if you see a pattern, yeah, you could. And so the p sub 5, they didn't ask us this, but I just want to see if you can guess what it is without having to go through all of that work. It's going to be everything the same. So I'm just going to write little marks to say that's the same. And then what would the next one be? Well, you might see that the terms alternate. So since the last one was subtraction, this will be addition. You might see that the fraction in front of the binomial always simplified to be 1 over something, and that something is the same number as, well, for the very last one, is the same number as the polynomial, like p sub 4. The last one was 1 over 4. So this one should be 1 over 5, and then x minus 1. Oops. Messed that up. Wrote a parenthesis when I meant to write a 1, x minus 1 to the 5th. And that's why once you get enough of these done, we hope that we can see a pattern instead of having to go through all that work each time. Okay, next example. Determine the degree of the Taylor polynomial, p sub n, expanded about c equals 1, that should be used to approximate the natural logarithm of 1.25 so that the error is less than 0.0001. And we're trying to find the degree of the polynomial, so we're trying to find n. Okay. So, to do this, I want to use what we just did and take it one step further. Do you see that fourth derivative? Do you think we could come up with an expression for the next derivative? Because the Taylor theorem that we're about to use needs the n+1 derivative. I think we can come up with that based on the work we've already done. Well, for one thing, the signs are alternating, so it's going to be -1 to some power, typically n or n+1. I'm going to assume n for just a minute, and if I need to adjust it, because I'm not getting the answer I want, I'll adjust it as needed. And the numerator, if you think about how those were created, the next one would be -6 times -4. No, I'm sorry. Yeah, would be 24 x to the -5th. And of course, 24 is a factorial, as is 6, as is 2, etc. So that numerator is something factorial. Let me think about this a second. If this is a 4 here, and this is a 3 factorial, that means that the factorial we're using is one number less than that n plus 1 that we have down here. So what's 1 less than n plus 1? Well, it's n. Okay. And by the way, we can go ahead and check that power of negative 1. Let's do that. Like, if I were trying to find the fourth derivative, then n, for that being 4 up there, n would be 3. So if n is 3, is negative 1 cubed going to give me the negative answer for the fourth derivative? Yes, it will. So that's going to work out just fine. And that's divided by x to what power? Well, when this is a fourth derivative, that's a x to the fourth right there. So that power matches the number of the derivative. So this is x to the n plus 1. Okay, so now that we've established that, using Taylor's theorem, the error will be the absolute value of r sub n of 1.25 and that means that our x, by the way, is 1.25. That's what we're putting into the natural logarithm function, is the 1.25. Will be equal to the absolute value of f, the n plus 1 derivative, evaluated at z, over n plus 1 factorial times x, which is 1.25, x minus c, which is 1, c is 1, so it goes in there, raised to the n plus 1. Okay, that's our error. And if we simplify that a little bit, by substitution, this is going to be the absolute value of negative 1 to the nth times n factorial over x, which is here what the z is. We're putting z into that. So z to the n plus 1 power divided by n plus 1 factorial and then 1.25 minus 1 is 0.25 to the n plus 1. Now, the power of negative 1, whether it ends up giving us 1 or negative 1, if we take the absolute value of either possible answer, it will become 1. N factorial is, by its nature, positive, and z, which is a number between x and c, where c is 1, and x is 1.25. Since z is that kind of number, z raised to any power will be positive, so I don't need to do anything because of the absolute value there. okay, times 1 over n plus 1 factorial. I just wanted to make that not such a nasty looking thing, so I'm taking that division and multiplying by the reciprocal, so as not to have a really nasty looking fraction there, times 0.25 to the n plus 1, which is positive. So the only thing that that absolute value did was it took away that power of -1 for us. Okay, so the n factorial and the n plus 1 factorial, as we talked about earlier, simplifies, but just in case you've forgotten how to do it, n plus 1 is bigger, so we start expanding the bigger one. N plus 1 times the next number down is n, stop, because that matches the factorial in the other part of the fraction. The n factorials cancel, leaving 1 over n plus 1. Okay, so this ends up being 0.25 to the n plus 1 over z to the n plus 1 times n plus 1, which we get from canceling the factorials. So, since z is between 1 and 1.25, this expression that we have, if I were to replace the z with 1, because it's not 1, it's bigger than 1. But if I were to replace it by 1, 1 to the n plus 1 is a nice number, is why I chose 1 here. Let it be 1, so it's right up against that interval from 1 to 1.25. So pretend like that's 1 to the n plus 1. I'm not going to write it because that's equal to 1 over n plus 1. If z were 1, wouldn't the denominator on the other side for a number that's bigger than 1 raised to the n plus 1, wouldn't that denominator be bigger than our denominator, which would make this fraction on the left smaller than the fraction on the right? And then we want that we've taken care of the z, kind of removed it by saying kind of a worst case scenario. If we were right at the edge of that interval and used 1, we can make this statement, and we want that in turn to be less than 0.0001. And solve that inequality for n, and you should get n is greater than 4.424 when you solve that inequality, which means we would need, if n is a positive integer and it has to be bigger than 4.424, we would need for n to be 5 to make that true. So we would need a fifth Taylor polynomial. That means n is 5. You say fifth Taylor polynomial. To achieve the desired accuracy when approximating the natural log of 1.25. Okay. This is a way you can determine just how far you'd have to go if you have an error or tolerance for error that's known like 0.0001. As long as the error is less than that, you're good. Then you can get by with just doing this through the fifth Taylor polynomial. You don't have to find the 6th, 7th, or 8th. You're going to be good if you stop with the fifth. And so that's what we were able to find here. Okay. So, example 6. Find the Maclaurin polynomials. And at this point, when I say Maclaurin, something ought to be popping into your head. I'll confirm in just a second what that should be. So we're finding p sub 0, p sub 2, p sub 4, and p sub 6 for the function f of x equals cosine x. And then we're going to use our last answer, p sub 6, to do something. Okay. Now, when I said Maclaurin, what should have popped into your head? C is 0. That's what should pop into your head when you hear Maclaurin. So, because we're going to go all the way to p sub 6, we need all of the derivatives through the 6th derivative. So, you start writing those down. F of x is cosine x. The first derivative is negative sine of x. The second derivative is negative cosine x. The third derivative is sine of x. The fourth derivative is cosine x. Roll this down a little bit more. The fifth derivative is negative sine of x. And finally, the sixth derivative is negative cosine of x. Okay, so since c is 0, we're going to need to calculate each of these, function and all its derivatives, at c, so at 0. Takes quite a while to write all this down, but this is the work that I expect that you'll need to do for these problems. Okay, so cosine of 0 is 1, negative sine of 0 is 0, negative cosine of 0 is negative 1, sine of 0 is 0, cosine of 0 is 1, negative sine of 0 is 0, and negative cosine of 0 is negative 1. All right. So, p sub 0 of x is f of 0, which is 1, over 0 factorial, which is 1, times x minus 0, because c is 0, which is just x, to the 0 power. And that simplifies to be 1. Now you might have noticed and maybe wondered why I'm not doing the odd ones. I'm going to do p sub 1 of x and show you why that's not a thing that we have to worry about. So that's going to be 1 plus f prime of 0, which is 0, over 1 factorial times x to the first. And of course, 0 times that means that it's exactly the same as p sub 0. And because we're adding 0 to it. So that's why we don't need the odd ones. They don't change from the one before. Okay. So we'll take our last answer and now do plus the second derivative answer, which is negative 1, over 2 factorial times x squared, which is 1 minus 1 over 2 factorial x squared. P sub 3 won't change from that. And so P sub 4 is our last answer. Plus the fourth derivative at 0 is 1 over 4 factorial times x to the fourth, which is 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the fourth. Okay, and finally P sub 6 is going to be our last answer. Plus the sixth derivative at 0 is negative 1 over 6 factorial times x to the sixth, which is 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the fourth minus 1 over 6 factorial x to the sixth. And so if you wanted to keep going, hopefully you see the pattern. They alternate sign, and then it's just the next even power of x with a 1 over that power factorial. Okay, so the next one would be plus 1 over 8 factorial x to the 8th minus 1 over 10 factorial x to the 10th, etc., etc., etc. All right, so then those are the polynomials we were supposed to find, and then we're going to use the last one to approximate the cosine of 0.2 using the 6th degree polynomial evaluated at 0.2, which is equal to 1 minus 1 over 2 factorial times 0.2 squared plus 1 over 4 factorial times 0.2 to the fourth minus 1 over 6 factorial times 0.2 to the sixth. And let me just pause for a bit of history here. Of course, calculators didn't come into standard use around, just in a household until probably late 70s, early 80s even for some people. And before calculators, to find the cosine of something like 0.2, you'd have to have a table of values, and somebody had to produce that table of values. They didn't have a calculator hidden in their pocket where they could just go off and figure out what the cosine of 0.2 is. So this is actually how approximations for those came into being, and somebody sat down and tediously went through all this arithmetic, and they found out, what degree polynomial would we have to go to so that our error is less than 0.0001 or whatever, so that their table would be accurate to those number of decimal places they decided to use. And then they just calculate a whole bunch of these like this. And of course, 0.2 raised to a power, just multiply 0.2 times itself enough times, and then say 6 factorial, do long division of 24 into that answer, and then do all the additions and subtractions. Very tedious work, but that's what historically happened to get all those values before calculators came along. And in fact, this is how your calculator does that arithmetic. The calculator doesn't know what cosine of anything is. What it does know how to do is when you say cosine, it picks up a polynomial like this one that I have for p sub 6 or maybe longer, and very quickly puts your number in so you get the desired level of accuracy. And of course your calculator can do multiplication, which is, division is just multiplication by reciprocal, so it can do division, and it can do addition, and of course subtraction is just addition of the opposite of something. So that's all your calculator does, is a bunch of additions and multiplications, which means you're also doing a bunch of subtractions and divisions. And that's all that's that you encounter in this level of this problem, is those operations. So this is actually how your calculator does this. So I thought you'd find that interesting. Anyway, if you do all of that arithmetic, of course you probably want to use your calculator to speed it up. You'll get 0.98006658. That's what that string of calculations gives you. And then if you go into your calculator and make sure you're in radian mode and type in cosine of 0.2, what I see on my calculator is 0.9800665778. So if you round to that last place that I got here, they agree to that stage perfectly, which means we're awfully accurate. They're not very far with this calculation from the actual value of cosine of 0.2. So that makes me feel pretty good about this. Okay, let's do our last example, example 7. And it says find the fifth Taylor polynomial for f of x equals sine of x. Well, by the way, I don't know if I said this before, but a Maclaurin polynomial is simply a Taylor polynomial with a designated special value c equals 0. Just wanted to say that. So when it's Maclaurin, it is a Taylor polynomial, but c is 0. For this one, we're asked to use c equals pi over 6. Okay. So what we need to start with is finding derivatives of our function down through, since it said fifth Taylor polynomial, we need to find all the way through the fifth derivative. So the first derivative is cosine x. The second derivative is negative sine of x. The third derivative is negative cosine x. The fourth derivative is sine of x. And the fifth derivative is cosine of x. So now we're going to substitute pi over 6 in to all of these. So f of pi over 6, sine of pi over 6 is 1/2. F prime of pi over 6. Oh, and yeah, by the way, you're supposed to know how to get trig values of pi over 6 without a calculator. So if you need help with that, please ask. Anyway, cosine of pi over 6 is square root of 3 over 2. Second derivative. The opposite of the sine of pi over 6 is negative 1/2. Third derivative, evaluated at pi over 6, negative cosine of pi over 6 is negative square root of 3 over 2. The fourth derivative, evaluated at pi over 6, is 1/2. And the fifth derivative, evaluated at pi over 6, is square root of 3 over 2. Okay, so the fifth Taylor polynomial, p sub 5 of x is the label for that. Make sure you use correct labels when you do this. Is f of c, which is 1/2, over 0 factorial times x minus c, pi over 6 is what c is, raised to the 0 power, plus the first derivative answer, square root of 3 over 2, over 1 factorial times x minus pi over 6 to the first, plus the second derivative answer is negative 1/2 over 2 factorial times x minus pi over 6 squared, plus the third derivative answer, negative square root of 3 over 2 over 3 factorial times x minus pi over 6 cubed, plus the fourth derivative answer, 1/2 over 4 factorial times x minus c, so x minus pi over 6 to the fourth, plus the fifth derivative answer, square root of 3 over 2, divided by 5 factorial times x minus pi over 6 to the fifth. And let's see what that becomes. 0 factorial is 1, so that becomes 1/2 times something to the 0 is 1, plus square root of 3 over 2 divided by 1 factorial, which is 1, square root of 3 over 2 times x minus pi over 6 to the first, minus 1 over 2 times 2 factorial times x minus pi over 6 squared, minus square root of 3 over 2 times 3 factorial times x minus pi over 6 cubed, plus 1 over 2 times 4 factorial x minus pi over 6 to the fourth, plus square root of 3 over 2 times 5 factorial times x minus pi over 6 to the fifth. And that would be an okay answer unless I say this. If I say simplify the coefficients, that means I really don't want to see the factorials and all that stuff, I want you to clean it up as much as you can numerically. When I say simplify the coefficients, that means that this p sub 5 of x, this will be our final answer, will be 1/2 plus square root of 3 over 2 times x minus pi over 6. Notice those didn't change because they didn't have any unresolved factorials in them, minus 1/4, 2 times 2 factorial is 4, x minus pi over 6 quantity squared, minus square root of 3 over 3 factorial is 6, 2 times 6 is 12, x minus pi over 6 cubed, plus 1 over 4 factorial is 24, times 2 is 48, so 1 over 48, x minus pi over 6 to the 4th, plus square root of 3 over 5 factorial is 120, times 2 is 240, x minus pi over 6 to the 5th. Now, simplifying the coefficients, you kind of lose the pattern. So the line above may be easier for following a pattern. For example, that denominator is 2 times something factorial, and that something factorial is the same number as the power on x minus pi over 6. The signs don't strictly alternate, so you can't do that, but actually they do go plus plus minus minus plus plus minus minus, etc. And then the numerators alternate between 1 and square root of 3, 1 square root of 3, 1 square root of 3, 1 square root of 3. So there is a pattern there, and if you needed to extend this without going through the process that we just went through to get there, if you could see all of those things, you could say that you know what the next one would be, and then you could simplify the coefficients as needed. Okay, so that ends 9.7. I will see you in class.